So we are trying to address the verification tool for all the work EPIC is doing right now with the AI stuff or physical-based model. So we have at EPIC, we have a GOAR team, which is Global Workflow Atmosphere River teams, and some of the folks are working in AI, some are verifications. So it's a lot of multitasking here. And I'm going to share, because this presentation in two parts. So I will be focusing on EVS, and Paul Madden will focus on WXVX, which is a Met2Go package. So with our whole NOAA and NOAA-EPIC PSL, GSL decided to go with EVS and WSVX tool as a verification tool for AI, NOAA, and even the GFS or other models. So okay, so what is EVS? EVS is EMC verification package system. So it's EMC is a lot of people like Environmental Modeling Center. This is a NOAA's center, so that's why it's called EVS. The core function of EVS is near real-time verification for operational model and product system. And this EVS is currently available on WCOS2, which is a highly restricted system, just used for operational system. So not on other HP, NOAA's HPC machines right now. Near real-time verification for operational model, it generally an extended version of METClass. The METClass is the core. It has all the, in the EVS, there are additional capability of new metrics and visualization. It also supports EMC model verification package. And there's a lot of other internal and external partner for this EVS development. And what EVS is capable to do is it wide range of investigate the biases in both operational and development model at EMC. And it's contribute to UFS model assessment as a wide range. And this is a product of EMC, and then they have a lot of diagnosis software for other components too, like Wave and other modeling component for verification. Just giving you a EVS brief outline. As I said earlier, it's based on Met plus core. It's totally a Python library based. And it generates a lot of statics file from Matplotlib graph. It's generated by, most of the graphics are generated by Python, 700,000 per day on NOAA's website through EVS. It has a nice web interface, display on EMC website. It's real-time update, drop-down menu. I just took this, just a courtesy from NOAA-EMC, what is EVS? Because we just got hands-on on EVS just a month ago, because it's just operational on WCOS2 machine. So we are trying to get on other NOAA's machine like Gaia C6, and we successfully tested on Gaia C6 machine, and now we are trying to port on Microsoft Azure for our larger verification tool to be utilized in our AI, NOAA, and other purposes. So yeah, this EMC, currently I just want to give you the framework for EVS, how, I'm not doing any demo right now, but we are just in the ongoing, work going on with this. So basically it just give a lot of score, kill score. It's usually global models, high resolution, regional, hurricane, air quality, all kind of applications. This EVS is used right now, and you can go to their website and and try to explore more about EVS. How we are trying to maintain for our work. we have our NOAA-EPIC EVS repository, and we are trying to do it right now on Azure right now. So we have an Azure branch, which is kind of pretty much good to go. Just a snapshot how much changes we have to make just to move from HPC machine to Azure. I was just looking at it. You can see my screen. We are keeping this branch as a separate branch. We are not merging the develop because there is a lot of ongoing work with the other HPC machines. So we are just keeping the separate branch. And you can see this is the changes we have to make just to run and to build successfully and compile successfully on Azure. So we have done a lot of modification to the original EVS, which was running on WCOS on Gaia C6. So well, you can see we have done a lot of changes. It's not just simple. You can do few modifications. You have to do really because in Azure environment you can see we have to do based on Azure specification. So we have done a lot of work has been gone into this. So we created this branch, and if somebody was interested, then you can go and check out this branch. But even though if you check out this branch, you need to download models, around 10 to 12 models, and then you just check out this branch and you can then compile it. So okay, so EVS is a global component. I mean, we are primarily focused on global because GFS, because in our AI model, we are using GFS and maybe some European. So we are just European models, but we are primarily focused on a global GFS, not regional. So global, so it has several components like mesoscale, seasonal, sub-seasonal, hurricane, AQM, CAN, but we are primarily focused on global depth. This is focused. So right now, because EVS, we are thinking of giving just giving an overview of how general GFS system is doing, and then AI model is coming to the picture. So that's where just let me see. Okay, so this is I just took it from EMC website. We are just still working on it. We are just putting the data, dumping data on Azure right now, and it's ready to use. But this snapshot, I took it from EMC website, and it's just a snapshot, and we are able to do it on same thing on Azure. And this is just one snapshot, but it's to wide range of statistical analysis across the model. Primarily, we are using grid to grid and grid to ops. And for ops, we are doing pre-buffer ops file, which is available directly on Amazon S3 buckets. So we are trying to make it run on Azure directly and getting the pre-ops from AWS S3 bucket. So it is then we're moving forward. Okay, and how to run this EVS is this EVS basically run in 3 main steps: prep, stats, and plots. So prep is like prepare the forecast and validation data, stats, compute verification statistics, and plots is visualizing the verification outputs. So basically this is job execution via cron job. It depends on your machine, but this is a driver, simple script, and then it will kick off based on this script. It will kick off Jeff's globe that prep, and that will kick off one by one, and this will the global data transfer will do the actual final job just to prepare the steps. But you have to do it 2 steps because we have to do first for grid to grid if you want, and if you want grid to ops, then you have to repeat the same step, but you have to change the configuration file. So we are still going through the steps and in the ongoing work. on Azure right now. We have already done on Gaia C6, which is another HPC machine, NOAA's machine. Once this is done, then we do the next step, and basically this is the driver file for Git 2 ops, let's say, because we are interested more on Git 2 ops to verify. So, and this will be kickoff using the cron job like this on this scripting. And finally, the plots up, and we have surface plot. I mean, this is originally designed to have 31 days to 90 days, but we are modifying it for our purposes. Like we're just keeping like 5 days right now for verification. We are modifying it, but this is how you to kick off the third stage, and it runs the 3-step basically. And it's fairly simple. It's not really complicated. Okay, so right now with the EVS and Azure, we have successfully ported on Azure, configured, built successfully. We are right now in the verification is in progress, and we are just doing the simple basic verification of GFS. And and we know to utilize Git to grid and Git to ops. And pre-buffer file, as I said, is on AWS, so we are just getting the file from S3 bucket. I'm just give you a little bit before I pass it on to Paul. I will say Paul is going to present on WSVX, a flexible particle forecast version 2. This is the tool which we primarily use for AI and MOI. The model output, because we are keeping EVS as an option right now. But EVS has a limitation. It's hard-coded on NSEP, I said, like WCOS supercomputer. It's required installation of nearly dozens of SPAC type models and perform this much verification. So the challenge is dozen SPAC type models, you need it, and and I showed you the code, you need to change a lot of stuff. So but we are keeping EVS an option right now. But WSVX has so many advantages, and Paul can go out it, but it support both physical based and AI based Python wrapper for Met and Met Plus, and which really reduce a lot of module dependency. And it's portable. I mean, it's very robust across the environment, and it's very flexible to use. So right now, EPIC will use primarily WSVX for AI animal framework, and now I will give it to Paul. We have our contacts, and please reach out if you have any questions. So now Paul can take on, and if you have any question, please put your question on your chat box, and we can go through that. Paul, you there or?
Yes, let me take over.
Let me stop sharing. All right.
All right, can you see this all right?
Yes.
Excellent. Thanks, Anil. So WXVX, as Anil mentioned, is a weather verification workflow tool. Some of the goals in the development were that this would be easily installable on any Linux system. So HPC systems, cloud instances, your laptop, wherever you like. So there's no assumptions made about particular modules, data, software stacks, etc., available from specific HPCs. You can run this anywhere. It leverages MET for the generation of statistics via a companion package called MET2Go, which I have some slides about coming up. Try to use best practices learned from the project I've been working on for the last year, so the unified workflow tools. That involves the task graph-based execution of all of the work, schema-validated configurations, so you can give users good feedback on problems before they happen, consistent logging, etc. It's built on community packages like UW Tools, Xarray, Requests. Where possible, we obtain data automatically and no more than we need. So for example, when we're doing grid-to-grid comparisons against grid-based analysis, we can pull individual grid messages across the network that we need without downloading much larger grid files. The code base is rigorously tested, including 100% unit test coverage. This is written in Python and distributed as a conda package, and hopefully is general enough that we can use it with a variety of ML models that we've been seeing. We are always expanding the capabilities. I've got some future work slide toward the end. So on anaconda.org, you can see the two packages that are involved here, WXVX, which is the workflow itself, and then Met2Go, which is the package wrapping the Met executables. In the lower image, you can see that we have builds of Met2Go, both for Linux 64, that's the Intel architecture, and also for ARCH64, which is the ARM architecture. So any Linux machine you're using, you should be able to install both Met2Go and WXVX. You can use Met2Go standalone. You could do this with a single command if you have conda installed, and if you don't have conda installed, you can get it in about a minute. The first command there installs the Met2Go package and takes about 40 seconds on my system. And then once you activate that environment, you're up and running. You have tools, all the tools from Met, the compiled executables, GridStat, for example. We also have all of the Python scripts from the base Met Plus package, plus a handful of scripts from other Met Plus packages. For example, this line.py is available from the matplotlpy package. Met Plus, something, I can't remember the name of the package. So a handful of those are available. They are executable directly. They're on the path. And depending on feedback we get from working with people in the future, we could either add more of these, or maybe they're not of interest and we'll slim the package by taking them away in the future. The package also contains data files that ship with Met and Met Plus. And when your conda environment is activated, you have a handful of environment variables available that you can use to access those sets of data. So for example, the Met data environment variable gives you access to data that comes with the Met distribution, and likewise for Met Plus Parm base. Those are some things that ship with Met Plus itself. This does make the conda package larger than I would like, so I'm considering making this an optional addition, perhaps a script that you can run that would download these things for you when you need them. That would slim down the package. But this is handy that things like, the poly files for masking regions during verification, those are available in your environment as soon as you create it. WXVX, the workflow package, is installed the same way. It depends on Met2Go and pulls it in when you create a WXVX environment. Again, a single command gets you up and running there. You can activate it, and here's the help from the tool itself. An important concept is tasks. We have high-level and low-level tasks in WXVX. The lowest level tasks are responsible for making grids available. Right now, we're just doing grid-to-grid verification. I'll talk about grid versus OBS later. But the lowest level tasks are responsible for making grids available for verification via Met. Baseline grids, those would be the truth that we're comparing against, for example, the HER analysis. In the case of some models, and then the forecast grids are pulled out of your ML data set. There's a higher level task that wraps both of those and implies them. So if you ask for the grids task, you'll get both baseline and forecast grids. Likewise, the stats task makes the grids available and then runs Met to produce the statistics. And then finally, the highest level task is plots, which will make plots from the Met statistics. Other command line options that are maybe of interest are check, which lets you verify your WXVX configuration before you run it and can point out configuration problems. There's support for threading concurrency, and you can ask it to show you a valid config file that then you can customize for your particular use case. This is a look at a very simple one variable at one level at one lead time from one cycle plot of the graph that WXVX would execute to get, in this case, plots. So the highest level task is plots. That implies two different plots, the mean error and RMSE for this 2-meter temperature variable. Those can be plotted from a single stat file created by MET. So there's a dependency on that single MET stats task. That then fans out to a forecast grid and a baseline grid task, and then they have their own prerequisites. The forecast task just needs the larger forecast data set that it can pull that grid out of. And on the baseline side, we obtain a grid message from a remote grid file via HTTP. And to do that efficiently, we rely on an index file that tells us where in that remote grid file to pull it out of. Looking a little more in detail at a very simple, one item verification task, we have the machine learning forecast. In this case, let's say it's ZAR, it's sitting on disk. We can think of this as a 6-dimensional data set where we have some number of variables, we have some number of cycles, each of which has a certain number of lead times. 3-dimensional variables have multiple levels, and then we have the lat and lon coordinates. High dimensional data, more or less, and we want to extract a 2-dimensional grid from that to do a single verification step. When we extract that, we also need to apply CF metadata to that file, which we write out as netcdf. MET requires data either in GRIB format or netcdf, and it's particular about the way the netcdf is formatted. So WXVX supplies the necessary CF metadata when it creates those files. And then on the baseline side, let's say we were verifying against a HER forecast, a 0-hour forecast, which you can consider to be more or less the same as analysis. The GRIB files that are available for HER correspond to a single lead time from a single cycle. So the dimensionality of that data set is smaller, 40, but in that GRIB file, you have multiple variables at multiple levels. So the procedure there is to retrieve the GRIB index. That allows us to find out the byte range of the message that we're interested in inside the GRIB file, and then make a special HTTP request to pull just that single grid from the remote data source. Once we have those two grids, we can ask MET to produce statistics. It may need to do some things like regridding. Let's say, for example, we have a lat-long grid. We have a model, I think either Daniel or Isadora showed this earlier. We had a model with a small domain over the Western US, and that was a lat-long grid. HER itself is a CONUS domain, and it's on a Lambert conformal grid. So MET needs to do a couple of things, both regridding HER to this ML model domain and projection, and also to mask the region. Once that's done, we have a stat file. And then if we scale up, even just considering one variable, one cycle, one level, this HER emulator had hourly output. So we had 24 lead times per cycle. So all of those need to be produced by WXVX. Then they can be combined, and then they can be plotted for a plot of a particular variable from a particular cycle. Obviously, and Vanderlei was talking about this earlier, the fan out of this is enormous. If you have 24 cycles per day with multiple lead times and a month of data and 10 variables, this scales up really fast. WXVX handles all of that with a admittedly very large task graph, but that's kind of the software's problem to deal with. One of the other problems WXVX is handling is the fact that there's not a lot of conformity in the output format of ML forecast data that at least I've been seeing. There's a variety of different ways that people are representing their data. So this is an X-array view of one data set. Things that WXVX needs to know are the cycle of the forecast, the valid time, or rather, given a particular valid time, it needs to know how to spelunk into this forecast data set and find the grid that corresponds to that particular valid time. It also needs to know about latitude, longitude, level, and things like that. In this case, this particular forecast data set has the cycle time, the init time, given by a coordinate variable called time. So that's pretty easy. That means that this data set can contain multiple cycles because it's indexed along this initialization time or cycle coordinate. It also has a lead time coordinate that gives integer offsets from that initialization time, and we can compute the valid time by adding lead times to time and then selecting the grid at that location in the multi-dimensional data set. Latitude, longitude, level, no surprises there. Those are common names. Mostly that's what I've seen, although I have also seen a forecast data set with just lat and lon as names. You'll notice the data variables here on the left kind of conform to GFS conventions, but notice T2M for 2 meter temperature. That's not a GFS variable name. They just use TMP for both 3D and 2D temperature variables. You can't do that in ZAR or NetCDF. You need individual variable names since you have different dimensionality of those variables. So that's one data set. But if we look at another one, you see different choices were made. In this case, the initialization time is not given by a coordinate variable, but by an attribute. You can see in the lower half of the left-hand image. That means that this data set can only contain a single cycle because there's no dimension for the cycle time. The valid time is given directly, so there's no concept of lead time in this forecast data set. We just have valid time specified directly for us via a variable called time. Again, lat, lon, level, no surprises. The variables in this case use something that look more like ECMWF names. And because there's only a single cycle here, the dimensionality is slightly smaller. We have 4 and 3D arrays instead of 5 and 4D arrays. And then finally, here's a data set that made slightly different decisions. You can see the data variables have very descriptive names, but they're neither ECMWF or NCEP convention. So to deal with that, the WXVX configuration lets us describe our forecast data set. This is just a part of the configuration, but we can see this forecast coords block gives us an opportunity to map kind of canonical concepts like latitude, level, longitude, initialization time, valid time to the variables or attributes that appear in the forecast data set. WXVX will prefer a coordinate variable if it can find it, but if not, it will fall back and try to find, for example, init time, initialization time. It'll look for a variable called initialization time. If it doesn't find it, it'll look for an attribute called that initialization time and try to parse it as a timestamp. So this allows us to deal with the complexity of the data sets that we've been seeing. It would be great if we had a convention and everybody's data looked the same, but I'm not going to hold my breath. You can do, since this is YAML configuration, you can do some nice things like reuse values via YAML anchors and aliases. We do that with the levels here to avoid repeating them. And then in the bottom half, you see the different variables. This is a mapping from variable names as they appear in the forecast data set to a more canonical description of what that variable means. So if we take 2 meter temperature, for example, T2M, that's the name of the variable in the forecast data set from the ML model. And what that variable is it's described in ECMWF terms as height above ground. That's the type of level it is. Versus, for example, pressure levels, which ECMWF calls isobaric in HPA. The name 2T also describes what this is, 2 meter temperature. So whatever it's called in the forecast data set, we can match it up to this sort of Platonic ideal of 2 meter temperature. And that also lets us look in the baseline data set. Let's say we were going to verify against GFS, it would allow us to find the corresponding variable in GFS that matches those same attributes. Other things in the WXVX config may be of interest. You can specify a projection for your forecast data set, the grids. The simplest case is a regular lat-long grid, but we had one model, for example, that used the same grid as HER, which is a Lambert conformal projection with a conus domain. And so we were able to describe that with a more complicated projection description. This gets passed on via CF metadata to the NetCDF files that are then given to Met to consume. The baseline compare on the right, this is an option that allows you to obtain forecast data for, verify, and plot data from the same model that you're verifying against. So for example, if we were verifying against GFS, we would have our ML model, but we could say we'd like the same valid time from the same cycle from GFS, and we'd like to also verify it and plot it on the same plot. So we can compare, for example, the performance of GFS versus its truth and a GFS trained machine learning model against the GFS truth. And you'll see an example plot of that a couple slides later. You can also apply a forecast mask. This is a rectangle. I think this is the CONUS domain, or maybe it's the Western US one, I can't remember. This is a rectangle. I believe MET also supports arbitrary polygons, so that should also be possible with WXVX because this just gets passed through in the right format to MET. That netCDF file that's created from the forecast data set to be given to MET, this is a X-array view of an example here. You can see in this case, the time dimensionality has been collapsed. So this is a single cycle, aka forecast reference time, single lead time, and we have just a 721 by 1440 grid. The rest of it is metadata that tells MET how to interpret this. So we have things like the CF conventions attribute set, which tells MET how to interpret this. We have a CRS variable that describes the grid projection. In this case, it's latitude, longitude, but this could also be a more complex value that would describe the parameters of the projection. Here's a resulting plot from a simple single cycle where we asked for plots. So again, the plots imply the stats imply the grids. So WXVX did all the work leading up to this plot. We have internally the capability to do some simple line plots in WXVX. So in this case, it was a GraphCast based model trained on GFS, and we are verifying this against the GFS analysis, but also we have verified the GFS forecast itself so we can compare the performance. So just for this one cycle, there were 80 different netCDF forecast grids that were created, pulled out of the much larger forecast data set, 122 GRIB index files and GRIB messages that were written to files, and 160 stat files created by MET. So obviously, when you have a much larger data set, this can get huge. Vanderlei alluded to this earlier in his presentation. I'll point out that the MET stat files, you could choose not to do the plots with WXVX and just run it up through the stats task. You'd have this collection of stat files that then you could analyze, visualize, et cetera, with any tool you like. Maybe the EVS visualization portion could be used on those stat files or different packages for visualization. Lots more information on the webpage for WXVX. Never enough documentation. There will be more, but I've tried to cover the essentials at the moment. Possible planned or future work. Next up is grid to OBS verification. There's very active interest in this. So this means making use of the point stat utility from MET. It's already available in the MET2Go package that WXVX is using, but we need to set up different MET configuration files for this. We have to figure out how to obtain the data. We'll probably need to support local paths for baseline data sets. Right now, the assumption is that we're comparing against grids that are in remote GRIB files accessible via HTTP, and that there are indexes for those available. Certainly, we're going to have use cases where we just have that data locally. Prep buffer, when we do grid to OBS, that's an open question. It's good to hear Anil point out that they have a bucket with some prep buffer data, but I don't think there's a really reliable, truly online archive of prep buffer data. NCEP ages theirs off. NCEI has an archive, but it's a process that involves making a request with a web form and getting an email. So we may have to put together our own archives of this for ML verification. Well, maybe we'll want to support GRIB forecast data sets. We haven't seen those yet. We usually get SAR or netCDF, but who knows? NetCDF baseline data sets. So again, if we used, I think, ERA5, for example, I believe that's distributed as netCDF. I could be wrong about that, but it seems likely that eventually we'll have netCDF baseline data as well as forecast data. More documentation, of course, and potentially more plot types. Although, I think there are other tools that do plotting very well, and we may want to look at integrating with those or giving users the option to take their stat files from WXVX and then visualizing those however they like. All right, that is my last slide. I will stop presenting and happy to answer any questions.
Yeah, thanks a lot, Paul. Thanks, Anil. I thought I heard one hand real quick. Was there any questions for either Paul or Anil? Okay, thanks both. Yeah, great work. We're looking forward to continue to see this advance. And yeah, thank you very much for your time. Oh, there's one question, John. Two questions.
I just put a question in the Slack. I could hold on, let me just pull it up. I can mention it here. I was just wondering, Paul, if you have any thoughts on sort of how to deal with the data management challenges with these AI models, which could be produce voluminous amounts of data, especially when you're running a lot of retrospectives, analyzing retrospectives, things like that.
Well, one unfortunate thing is that unless you're, if you're producing ZAR and NetCDF data, well, by the way, I don't think Met can consume NetCDF directly at all, or sorry, ZAR directly right now. It's not hard to convert, but that means making a copy of the data. And if you had NetCDF and it was perfectly formatted for Met, we might be able to do less, have less data on disk. As things stand, when WXVX creates these small standalone NetCDF files, once you have a collection of those, you could then run, if you wanted to produce different statistics, et cetera, you could just keep reusing those. Yeah, it's going to be a lot of data. If you have a lot of forecast data, you're going to have a lot of verification data too. Yeah, I don't have any good answer to that, unfortunately.
And Paul, there actually are a couple questions in Slack. There's 3 to be exact. I just posted the first one, and then I'll post the other one since we have another couple minutes if you have any insight into those.
Let me pop over to Slack.
Yeah, and the first one was my question. Sorry,
it was.
Skip
Okay.
that one.
I see that now. Yeah, the next one is why not just use WXVX instead of taking 2 systems? Is the next question, Paul.
Is that in terms of the work that Anil mentioned using EVS? What's the second system?
Yeah, I think that's what the question is for. Why try to port EVS when WXVX works? Right.
WXVX is a fairly new development. I think it's pretty robust, but certainly EVS has more history. I think covering, maybe Anil would speak to this, but I think they did want to cover all bases and make sure that they're not taking more risk than necessary and have some options. It does sound like from what Anil's saying, they're leaning toward using WXVX, at least for the statistics generation part. I don't know, it's put all your eggs in one basket. Maybe that's a good idea if you guard the basket very carefully. Hopefully that's what we're doing with WXVX.
Yeah, and EVS currently, we are just keeping the option for right now, but we are moving slowly towards WXVX. So with our program managers, they want EVS currently and an option, and we are just working on that. So in coming months or future, we may move completely to WXVX.
Yeah. Thanks. And I think the last one was more of a comment for either Paul or Anil. I guess, Paul, for your verification, there's a verification website that flashed by in your presentation. Can you just drop the URL in Google Chat for that? I think that was just the last comment.
Is that the URL for the GitHub repo for WXVX, or?
That's from Jessica. Can you clarify that? Is that the one you're talking about? We can take that one offline in Slack for the last one there.
Yeah, there was an EMC verification website. So I put some QR scan code, so probably.
Okay, she said yes, that is the one. So I will tag either of you in Slack if you can just drop it there. That'd be helpful. Thank you.
All right, thanks.
Thanks, Kevin.